one, and all the people that argue all the shit back and forth, right? They're just arguing for their ego, and it's essentially like their interpretation of the one, and it's like a hallucination. Why do we need the one? I'm going to go back to that. What's the inherent necessary value like that the one incurs? Why? It's a coherence or something? Like, what is it? Why can't it be the many? Like, if you look at any sort of feat of creation that human beings are attributing themselves towards, it comes to from the, what do you call it? The works of many people coordinating themselves together.
Yeah,
Kind of
but at
like
one point before we were many people, we were few people. And if we follow that trend, we go back to very few people, all the way back to maybe one people.
maybe
I mean,
one
it's just a
people,
logical
or
deduction.
like, are you entertaining the garden, or are you basically out of Africa sort of situation?
No, you ask why we invoke this oneness or whatever. Well, that is just because when you try to trace things back, like now we are 8 billion people. 100 years ago, we were 5 billion people. And if you follow that trend, we come back to
How do you know
a
that?
small population of people. So if you follow
don't know
these kind
that,
of things, like things start out simple, becomes more complex, and all these kind of things, this is what we have precedents for when we go out and analyze the world. So we have precedents for same things starting out small, like a one, that separates it into many.
Your assumption is
Well,
the
I do
truth
think
of
it's-
history, dude. Like
Well-
history, like you can't necessarily know whether or not history is absolute. And if you're going to base it on that, like, we're kind of cooked.
Well,
I'd have to bow out because
I invoked things in the last 100 years, like just that example of going from 8 billion people down to 5 billion people in a very short period of time, a very well-recorded period of time. So if you follow that trend, entertain it, we come down to, a simple start with few people, one society that grow up and had this technology and stuff like that. Everything that we analyze in this world start out simple and become more complex over time. They don't start out complex and become less simple over time.
There were bigger beings. So you're saying like we're becoming more complex, or are we simplifying? What's your prognosis?
Bigger doesn't mean more complex.
Bigger? I mean, like, is the notion of the mind sort of an emergent property? So it's becoming more complex. Is the universe becoming more complex because of the nature of the mind? Or were like animals that were larger in the past, like more complex or something? Like, because we know that we got big bone shit in the past, right?
I guess I refer back to what I just said. Like, big doesn't mean more complex.
It doesn't mean more complex. So bigger doesn't mean more complex?
No, you can take a little
big
stick,
with less parts, smaller with more parts.
and it's the same,
That
just
can
different
exist.
proportions. The complexity of a little stick and a big stick is the same.
Okay,
Well, they could be bigger and less complex, and smaller and more complex.
Yeah, I mean, reptilians, dinosaurs, small brains.
What is
compared to
more
the body?
Yeah, but you got a humpback whale with a brain the size of a mini car, much larger than ours, but apparently, we're smarter. So is that more complex? Like, how do we delineate these things?
I just think the humpback's setback is that it doesn't have thumbs.
Sorry, it doesn't have what?
Thumbs, the one finger that allows us to carry
opposable digits.
Yeah.
Oh, thumbs. You think thumbs are the game breaker, like in the material world, right? Like the thumb is the causal aspect that allows man, like what? The manipulation of matter to an understanding, like
there is
tentacles are pretty cool.
There is three main things that made humans successful. If you go with the evolution story, and that is one, the thumb, 2, big brains, 3, overhand throw. That's the 3 things that separated us from everything else.
Well, as far as like our evolutionary development, I mean, what came first? Did the thumb come before all of the other useful items, like the complexity of the eye or the ears, our vestibular system? You know, like there's all these other conventions in our utility belt, but you're saying that the thumbs were the most advantageous. You know, it's just another appendage. Like, so if it was just an appendage, did this come before the other items, or?
Yeah, can you imagine if
again,
God said, like, let them have thumbs, and that, like, therefore man was created? Like, it's just a consequence of the thumb.
Wait,
all of
apes
the
have got
stuff that we
thumbs.
talk
I mean, I
about.
don't get how you
shit.
can't see it. Like the ability to hold things in your hands separate you from pretty much any other animals in the control that we have with the thumb. On top of that,
I just said
no other
apes have
animals
thumbs.
can throw things
Yeah,
over the
Dub.
head, which means that we can throw these spears, these things that we're holding
Apes,
a long distance.
apes.
They don't fucking overhand throw.
Dude, Tim, like, T-Dub just said that monkeys have thumbs. So, I mean, what's going on?
But they lack other things, like our brain,
Like what?
our developed brain. They also lack overhand throw. So whatever they are holding,
They probably think the
can't even
same about
use as
you.
anything but a battery stick. They can't even throw it. We were successful because we made bows and spears that could kill things at a range.
Okay.
We need that
So,
overhand
like,
throw. If we didn't have that overhand throw, we would not be here today.
So why didn't we take out the other monkeys then? Like, because we've become more dominant because we got overhand throw and we can shove a javelin.
Yeah, some of them are bigger and scarier. I'm gonna tell you
Have you
what,
ever
they didn't need
Like,
us.
we took out the Neanderthal for some reason, and we just let the other monkeys alone.
Have you ever seen these videos of like people who don't have arms and they're just using their feet for everything? You see them cooking in the kitchen with their feet. You know, they're doing all this activity.
Let them go hunt. Let them go hunt.
Dexterity.
Build cubby houses.
They're just very ingenuous. You know, like they make utility with what they have. But you're saying that the thumb, you know, the advent of another appendage made all these other things possible, but people would just accomplish them however they could, you know?
But take that same person without arms and now put him in a wilderness situation and he has to kill something for survival. The guy without arms, no matter how good he is at adapting to modern conveniences, doesn't matter in that situation. He did.
Dude, I promise you that a guy without arms could figure it out. There's going to be one badass, Biggie badass, is going to figure it out.
You could definitely kick your ass.
Well, the exception doesn't make the rule, right?
Well, I could say that about your theory.
But my theory is not about an exception. That's the common trait that we all have and share. And
well, you labeled mine the exception. You labeled mine the exception, but I promise you, all these people with limited abilities are getting shit done.
Well, you actually made the exception yourself because you said there would be that one badass. So you made the exception.
The one guy who didn't have arms. like all the guys without arms are going to be doing badass shit, but I only know one of them. You know, there's just less of them. That's all.
There's a market for unicycles.
Yeah, look, what about clowns? Plenty of clowns around.
What about clowns? Yeah, look, I'm just saying that, like, perhaps, let's just be honest, you might be limiting our potential just slightly. Like, you might be just self-limiting for the sake of narrative. But in every iteration of our development, we're very fucking useful. You know?
Can I present the alternative, though, Riggs? Have you ever heard of... it was a big thing, like, I don't know, 10, 15 years ago or something? Like the dog girl, like the girl raised by wolves. Are you familiar with that story? I don't know if it came across America or not.
I've heard of something like that with a guy, but I mean, it's often like the story of a movie or whatever too. So I don't know.
like just is like on the media. This girl that was basically like, abandoned or some shit, and like raised by dogs, and she's literally walking around on all fours and like just like odd shit like that. I mean, what am I to say about that? Is the opposable thumb the causal aspect of our intelligence? So what is it? Grasping things? So therefore, like manipulating matter? I don't know, man. They come up with these wild stories though that come in the media. Like I said, with the dog girl or something. She's behaving like a canine, essentially, simply because she was raised in that situation. It could be just like a psyop or some shit,
Yeah, I haven't heard of the wolf girl. I've heard of wolf man, wolf boy, or whatever, raised by wolves. Common trope.
That's Mowgli, right?
They had this. The thing I remember on the screen was essentially this contorted young girl, probably sort of young adolescent sort of situation, and she's sort of walking around like on all fours, and her body's like discontorted, and like even barking, right? Like weird shit like barking. That's a mad story for a while there. I haven't thought about that for such a long time. It's like what the fuck was that? I'm gonna look it up.
Yeah, I could look it up. Let's see.
I heard she was a real bitch.
Get it?
Okay, Amala and Kamala are the most famous, though debated, cases of children allegedly raised by wolves, discovered in India in 1920. And there's other ones. There's one in Ukraine, Oksana
Ukraine one.
Malaya.
That's the Ukraine one. The one that I think that is the one that I was thinking of that came to my imagination, like just this old story that was on the headlines for a while. 60 Minutes Australia, they did a big thing on it.
Yeah,
Raised by feral dogs.
Post the name. I will also post the summary here.
Diagnostic presentation at time of rescue. Locomotion, exclusive quadrupedal movement. She was walking on all fours.
Yeah, I see a picture here.
Canine mimicking vocalization, so she was barking and growling. Lack of human language at all. Like I don't know what the fuck is happening in the Ukraine, but I don't know, man. I haven't thought about this in a while, but that's a psyop. I don't know what to think about that one. Dude, do you really think that a human being could be raised by wolves? Like, do you honestly think that you could leave a small child and they would just? I'm not sure.
Well, if they think that you're part of the pack, then there is some potential there. But the validity of the story, I don't know. Also, I posted another link with this person, and just take a gander at the thumbnails.
Yep, that's the one. That's what I remember seeing. And she they've got her wearing like an orange shirt with like denim short pants or something. Something's going on here.
I mean, just also look at the facial expressions. You know, like they clearly weren't raised like looking to or trying to receive approval from humans. because there's no like exercise of the facial muscles. It's just very, very flat. The look on the face is very flat. I'll take there's a picture here. I'll share it.
Kill it.
Russian child, Oksana Malaya. This is bullshit, bro.
I don't know. Maybe.
This is bullshit. Look at like just the link that you shared. That all that's interesting.
Do it.
What did you say, Roohif?
No, I'm talking to Sage.
Oh,
1 second.
Sage said, "Do it now." Do it.
hey, we were talking to see the name gravitational
Ritsky mentioned
container.
that Oksana Malaya was walking around on all fours and mimicking vocalization, indicating she was barking and rolling with a lack of human language at all. This isn't a shouting match.
Anyway, gravitational container. What's up?
Yeah. No. I just wanted to get like a quick admission from any gravitational proponent that even in your paradigm, gravity is the container, correct?
For the atmosphere, yeah.
Yes.
I don't like to use
So-
the word container for it because it's generally used as like a physical container.
Well, do you agree that the water on one side meets up to complete the circuit on the other side? It's an infinite loop of water due to gravitational
Sure.
containing. Okay.
Yeah,
So
gravity
even in
keeps
your
water in Earth, yes.
worldview, even in your worldview, gravity is a container. Therefore, you need the container to have some sort of baseline for pressure measurement.
That's why I don't like using the word container because
I know you don't like to use
it-
the factual term.
because Flurfs use it as a physical barrier when it's not really.
Well,
it
even-
restricts. A container restricts volume, right?
Sure, but I don't
Is
think
gravity
it's
restricting
what
the volume?
people mean.
Gravity's
I don't
restricting
think
the
it's
volume,
what-
right? It's a container.
I don't think.
Yeah.
Okay, I'll get my sentence out. I don't think it's what Flurfs mean when they say pressure requires a container. I think they're more referring to a firmament, a physical barrier.
Oh, so you want to straw man the position for the sake
Yeah.
of preferring the argument that you like, rather than
If you
the
want to say
facts of the
gravity
matter.
contains the atmosphere, I'm happy with that.
Hey,
Cool. Don't need a barrier.
you know what? I think cups contain the atmosphere. I think the Mariana Trench contains the water. I think gravity is a container in your model. So in both models, they're being used as a container. So in every essence, you need containment to measure pressure against.
Cool. Do we need a physical barrier?
The water
not
is the
gravity.
physical barrier. The gas
No, the
pressing
atmosphere.
against the other gas is the physical barrier.
No. Why doesn't the atmosphere, shoot off into space? Do we need a physical barrier to contain it?
Well, this
you've
isn't
got a
about the
force.
top.
Right. I agree we have a force. The question is,
This
do we need a
isn't
physical
about
barrier?
the top. This is about the sides.
What?
This isn't about the top. It's about the sides.
What are the
Okay.
sides, Riggs? I don't know what you mean
sides,
by that.
well, the water-
looping Earth, right?
The loop. The water is meeting
Yeah.
up to the other water, causing a barrier, right? And then the gas is meeting up to the gas, offering a barrier. And then these barriers have fixed volume because of the pressure. So
Right. Does gravity
only reason-
explain why we can have gas pressure next to a vacuum?
The question is,
Does it
does gravity actually explain the curve, or could it just be a force that's coming down from above?
On a flat Earth, you can have gravity. Yes, it just means you've got a really big flat Earth. That's fine.
Winning.
Yeah.
Here we
Cool.
go.
So the question was, does gravity mean that we do not require, does gravity explain the fact that we have gas pressure next to a vacuum? Does that negate the need for a physical barrier?
Yeah, but whatever, like beyond the, within that vacuum, like, good luck, bro. A place that man has never gone, that
Well,
like
you don't think he
material
has.
substance, like break down, like, no. You just think that man can go there, and I mean that's your proposition, and you have to deal with the fact that your substrate
You have to deny all the
can't
evidence.
exist
He's
with
right. It does. I mean, it does explain it. I mean, if everything like that was true, right? I mean, Superman coming from the planet Krypton explains why he has superpowers.
Cool. So we don't, when Flurf say gas pressure requires a barrier, you can't have gas pressure next to a vacuum, and we say gravity, that's an explanation, right? The fact that there's a force going down.
Not interesting explanation.
I'll be frank. I
Interested
wouldn't
in the
argue
proof
it.
of the explanation. That'd be cool.
Yeah, I wouldn't be arguing that line of thinking. I think, yeah. So when you say Flurf say, whatever.
Gas pressure next to a vacuum.
Well, what is the vacuum? Like, I mean, in the cosmology of the so-called flat Earth, what is beyond the thing that we have any necessary sort of tangible information that you and I can inform ourselves on beyond like what we're seeing through a screen and a set of like calculations and mathematics?
Well, you can send up.
I don't find that substantial. Yeah, you can send up a balloon. I mean, it's not going to get you into space. You know that. I know that. Why do you pretend like a balloon's going to solve the problem?
Well,
they just redefine where space is.
Well, there's no such thing as a perfect vacuum, right? So there is a somewhat arbitrary.
No one ever
point.
said anything about a perfect vacuum.
Well, my point is that there is a somewhat arbitrary line where you say this is the vacuum of space. And you can set that wherever you like, but you can send up a balloon and easily get to a point where 99.9% of the atmosphere is gone.
Okay.
And
what does that prove?
I'm happy to call
it a vacuum. What does that prove, though?
You can easily get there, guys. Easily. Just get there. There's a line.
Good morning.
Hey, Issa.
Yeah, so it's not a...
What is this?
Yeah.
Go ahead.
Sorry. Go. Oh, yeah. So like, it's not about the downward force or like the top of the cup, bro. It's that like, in my argument, the cup has the walls and the walls are the containment, right? Don't care about the downward force, whatever. In your paradigm, the water meeting up to the water on the other side, the gas meeting up to the gas on the other side, etc. This is the container. So in every instance, you need containment to have the pressure. Thank you.
Okay. Again, that doesn't sort of relate to the evergreen meme of you can't have gas pressure next to a vacuum.
Where does gravity come from, Roohif?
I don't know.
Well, great. I mean, we can admit, okay, we can both agree that we do not know where the down comes from, right? Can we? Right. We're going to try to establish some facts here. We agree upon the down. The question is whether it's converging, parallel, or diverging, fundamentally.
For this argument, it doesn't matter.
No, why doesn't it matter for this argument?
Because regardless of whether it's radial or flat, it's down and it holds the atmosphere on the Earth, regardless of shape.
So your argument is like mostly against the notion of like container needing a surface of container. Like, but I thought we already agreed like a little bit earlier on that like the notion of container. I mean, I'm a little bit more flexible than the guy that says that I need a lid over my jar. Okay. I think it's a like electrokinesthetic sort of action that's going on. So I don't need and all I need is a Gaussian surface above. Yeah, for the electromagnetics to properly work, you need like two Gaussian surfaces, transpond like cathode and an anode and a cathode.
Okay, I'm going to use my heuristic at the moment, and I don't know anything about Gaussian surfaces.
They're just like they're electrically porous surfaces that allow electrical flow, and it's the distance between them that creates the resistance. Get Andrew in here; he'll probably bore us to death with it. But essentially, that's all that's going on.
It's a wireless
Andrew
energy transfer.
Okay, but when you talk about electrostatics, I'm going to say, all right, show me Coulomb's law creating 9.8 meters per second squared. You can't do it.
I've heard of Coulomb's law. I'm not sure of like how you're invoking it right now.
It's kind of the equivalent formula to gravity, but with electrostatics.
It's the equivalent equation to gravity, but it's about electrostatics.
Yes. So a different constant.
And so it works.
Yep. But you can't get a 9.8 meters per second squared out of it. So it can't explain.
What can you get out of it?
The attraction or repulsion between two charges and the distance between them. Same as like the attraction of two masses and their distance between them.
Is it in that electrical value or exchange? Is that AC, DC? Like, can you tell me about the frequency?
A static charge. It's a static charge.
A static charge means like pent up, held. Like static is held up charge. You like saying something's a static charge is basically saying that it's like a battery. It's a static charge. It's holding that energy. What does it mean? What do you mean? How are you invoking this?
When flat earthers say it's not gravity, it's electrostatics, there are well-defined formulas to work out the force between two charges. Right? It cannot be done where you have one object has this charge, another object has that charge. Can I match reality and get a 9.8 meters per second squared acceleration out of it? Can't.
Okay. Is matter made of positive atoms, like positively charged atoms?
And negatively and neutral.
Yeah, but atoms are made of positive charges, right?
And electrons are negative. You got more electrons, you got an overall negative.
And then the Earth is negative.
Right, but you've got other things that are negative as well. They should repel. If I have a negatively charged object in my hand, if I add some electrons to an object, it's negatively charged, and you're saying the Earth is negatively charged, therefore these two objects should exert a repelling force. It should float.
Well, you're assuming that all electricity is like what? The same type?
What do you mean the same type?
It comes down to frequency, like the way you pulse the signal. There's an interesting phenomenon going on.
I don't know if Tank is here, but he was saying that there's 8 different types of electricity. So to assume that one would even interact with another one is not correct. So like to have a negative next to a positive doesn't necessarily mean they operate within the same, in the same function, I guess.
Yeah, I suspect at large, when you get down to the rhythm on the frequencies of electricity, it's kind of like a symphony orchestra. There's a bass tone, a high treble, and all of these other things that are going on within the phenomena. Just to say that electricity is a sort of oversimplification of the process. There's so many other things that are going on with the frequencies.
The frequency of what? These are all words.
Great question. I love that question. Thank you.
Right.
Frequency of what?
Yeah.
Thank you.
These are all words that you're saying, and I'm trying to apply it to electrostatics, and I've got no fucking idea what he's saying.
Well, it would be a persistent medium, right? Be something there.
Frequency electron.
Whenever we're invoking just frequency, I don't know if somebody was talking.
Frequency of what? Frequency is a property of something, not an object.
Excellent. So, yeah, I would say the frequency of etheric perturbation.
Okay.
Persistent medium vibration.
Right. Persistent medium. Well done, Sage.
Are you?
Could you rephrase that?
I said, well done, Sage. You write down, Riggs, the frequency of etheric. Oh, what's it doing? The frequency of etheric perturbation, some or other.
Yeah.
That was fantastic.
1 sec.
Thank you. I guess it's just basic. You asked the medium.
What's etherical perturbation?
Yeah, so
Are you like the frequency of etheric perturbation somewhere or other? And Roohif responded, I said, well done, Sage. You write down, Riggs, the frequency of etheric. What's it doing? The frequency of etheric perturbation somewhere or other.
Hang on. Sage is having a moment.
Fucking bitch. Shut up.
There's a fucking Bronco over here.
It's super interesting though, right? Yeah, if there is an ether, then you perturbate it, you get a little vibration going, and you can sense things on the other end, That's kind of the idea.
How about we get a little Coulomb's law?
It's a necessary requirement for light to perturbate. Absolutely. Has to be. There is no way that you have a substance that you call light that behaves like a wave. It requires a substrate by which to actually propagate through. Period.
And then just look at how it interacts between like glass and a vacuum, and I mean, if anything, the signal just gets better. So I think it makes the most sense, man. Like how does light operate as a packet of energy? If it's got no medium to pass through, there needs to be some sort of energetic exchange. It goes through the glass, goes through the vacuum, through the glass on the other end, and pops out just as it's normal. And that only makes sense if there's a persistent, finer medium than gas.
Like what is between, like you've got like gas and they're energetic, there's space in between the gas molecules. What's inside the space in between the gas molecules? Is it so preposterous to like propose? It's not empty space though, is it? Like it
what
has
is empty
these
space?
charged. Exactly. So like when you say that you go up like so many miles above the surface of the Earth and say, oh, like empty space, there's like semi-vacuum or whatever you want to call it. Like no, you're still propagating these. What do you call it? Like it's. I don't even know. I can't think of a cool term. Go ahead.
We're talking about whether there's pressure.
Effervescence.
There's not.
That's what I would say. It's like this effervescence that sits like within like all of those molecules that you say like in the space between the air. There's something else going on inside of there. Poetic.
Cool. I think Dawn. Yeah, got it. I can't think
Dawn
of
got what? Chlamydia? Like, what did you get, Dawn?
Yeah.
Hey, what's up, Dawn? Good morning.
Can you make the air be 70 psi whenever you want?
What's up, Dawn?
80 and 90. Because like if it's held by a container and it's 14, then you just start making air, pressure, heat, then it should be like 57, 90, 120. We've never seen that, right? You've never had to be able to hold any more gradual pressure in this atmosphere, like keep it locked in, have you? You just got the magical 14, which you don't even know what that means.
What's up, Professor Phil?
Professor Phil.
Hey, how you doing?
Just giving him a little talk on Coulomb's law, which I imagine you're a bit more familiar with.
Here we go. He's got a professor, but dude, Roohif, impress Mr. Phil about your Coulomb's law knowledge. Let's go. So we can poke some holes in this shit.
Attractive or repulsive force between two static charges based on their The distance.
Stop talking about your personality and get to the substance of it. Like, what are you talking about?
It's
KQ1, Q2 over R squared.
Yep. What is K? That's in the chat. K's in the chat.
K's the constant.
Yeah, I know, but it's 1 over 4 pi times the permittivity of free space, apparently.
Look at these nerds getting along. Okay, rock and roll. Okay, the
permittivity of free space, mate. We've got permittivity of ether. Now we've got permittivity of free space. What the hell's that?
Yeah. Oh, empty space, whatever.
Free space, solidity container. You have a free space container. This is awesome.
So, Professor Phil, Rixky said the Earth is negatively charged.
I'd ignore that too.
What force, which direction should the force be if I'm holding a negatively charged object in my hand and the Earth is negatively charged?
Depends on how negatively charged. You can't just say, it's negatively charged and another one's negatively charged. There's a difference between the two.
No.
That's how you establish. Like, if you're using a multimeter, it doesn't work unless you find a neutral ground. You need to find a neutral ground, and then you compare it to
we're static charges.
System
You've also got repulsion.
There's no grounding.
You got repulsion with the same thing you're talking about, as well as acceptance with magnetism or electromagnetics, or static or diamagnetic electric. So, everything has that property of being repulsive or attractive through the electricity. What you don't have is mashed potatoes and Jell-O doing it through the electricity.
You can get the potential between two poles on a battery.
Can you guys levitate with your gravity electricity? Some Jell-O and some mashed potatoes.
Don't worry about the Jell-O and mashed potatoes for a second. What is the notion of presenting the fact that you've got a positive and negative on either side of a battery? What does that mean to the causal aspect of the conversation we're trying to have?
Okay, so basically,
about essentially containment. By the way, we're looking for containment.
So basically, what's happening is you've got chemical potential, and every time once you make the circuit, this chemistry begins, and what it's doing basically is moving electrons from one side of the battery to the other. So from the negative part of the battery to the positive part. So as electrons are given away by whatever process you're doing, if it's nickel or lithium or whatever, it doesn't matter. It's giving away electrons. It gives away electrons. Electrons go from the negative part and end up in the positive. And
I didn't know that.
And eventually, all that happens is as the electrons,
not yet.
As the electrons get from one from the negative to the positive, we are aware of this and we use it. And we say, well, if you're going to go there from here to there, can you just turn the lights on your way? That's it.
That's the funniest explanation I ever heard.
That's a fact.
Well,
you're getting the electrons offer you some sort of courtesy if you can turn some lights off or something. What are you talking about?
Well, I'm just giving it a bit of
creative liberty at the end of that. Okay.
Yeah. I mean, the electrons don't say anything, but you do use the electrons. The electrons are going to go from one side of the battery to the other, whether you like it or not. So
no, you don't you like it or not. You're saying they're electrons. We know that there's some sort of force going on, right? There's a potential. What do you call a battery? It's static. I think Roohif invoked this terminology. It's a static.
Do you understand? No, it's not. That's not what happens. There's a potential for the chemistry to happen. A chemical reaction is about to happen.
What do you mean? There's a chemical okay. Next.
About to happen, but it's all in the battery, not happening yet.
I thought he had more to say or something.
Me too.
Chemical reaction.
It's about to happen.
Let me cut off. Let him know he cut off.
You have an oxidation reduction. You have an oxidation reduction reaction. That means electrons are going to move from one element to another, right? So in other words, one element is going to be oxidized, the other one's going to be reduced, and then as that gets reduced, it causes electrons to move. And those moving electrons, you can take advantage of the fact that they're moving and get them to do something while they're on their way.
Okay, so do you agree, Mr. Phil? Sorry, is it Dr. Phil?
Yeah.
PhD
Yes.
Phil? It seems weird to call someone Dr. Phil because of the Americana sort of shit. Okay, my apologies. But when we measure the sky and we put a node, like a copper node, up in the sky, and then we have one on the ground, we measure a voltage differential, like a potential, right there, right? So that indicates that there is a flow of, would you call it electrons, from the sky down to the ground?
No, definitely not.
Okay.
No,
why not?
Definitely not. All it's saying is that the potential up there, where the sky is, potential on the ground is a certain amount of volts. That's why it's called potential difference.
No, but it's seeking equilibrium, and when you actually short circuit the system, you can see the voltage potential between the different, so up high, and you short circuit the system, you can basically see the voltage potential pick up. That actually does inherently imply that, like, from the sky down to the ground, there is a constant flow of energy.
No, there isn't.
Because you're picking up the voltage potential. Yeah, because you're crossing the resistance. Like the atmosphere is a resistive sort of flow of, what do you call it, like force down below. How do you say no to that? Like, what am I saying wrong exactly?
Okay, you're misunderstanding what's happening, okay?
If you say so.
Yeah.
Do you want to describe to me how I've misunderstood it? You got voltage potential, right? You can measure the voltage potential. Okay, come back in a second. So essentially, like, we have a voltage potential between the sky and the ground, measurable all the time. Like, anyone can do this. Now,
so
all
like
that implies is that
the ground doesn't
resistance.
necessarily need to be negative, though. Like, it just needs to be less, so that there's a flow from high energy to low. So it doesn't necessarily need to be zero or whatever. I think it's a misconception.
It doesn't. Yeah, it doesn't need to be zero. It just needs to be less than. But like in our universe, there is no more ground than ground. Okay, like it is considered to be the zero. I don't actually know whether or not you could get below. Like, if you could stick a node into the ground and then get below that ground, like that voltage potential, I don't think you can do that. The ground is the ground. You got to ask Andrew for that. That'd be a really interesting question, actually. There is no lower like voltage value than what the ground is. You can't get below it. Like, is there any machinery that we could produce to go below the voltage of the ground? I'm not sure.
I didn't know that.
Yeah, grounding rods.
I mean, I don't know if that's true either, but I'd never heard that before.
It's just the absolute. I didn't even think about it, man. Like, it's just through the course of the conversation that it just sort of emergent of it. Like,
it seems like it's more than that too, right? When you got the way he's explaining it, and you're explaining it to him, I swear to God, it doesn't seem any different than radiation or anything else that bleeds, or the gassing effect, all gassing. We keep saying chemical electrolysis. That's just basically when you put these things together and you get the reaction. So the energy,
The question you ask, I don't know. It just maybe the way you're asking is, my head goes, no, I don't understand it. So you saying is that the ground must stand on top as a zero charge? Less than? Is that what you say?
can you repeat that? I'm not capturing the whole thing.
No, that's my issue too. I'm not really getting what you mean. What you mean? Ground is an absolute. You
can't get any lower voltage than what the ground is. That you, like, in the notion of a vacuum, like you live in like what we call like 1 atmospheric pressure or some shit, right? But we know we can build a chamber, pull out the air, get a lower vacuum. The question is, actually, can we get a lower voltage than what we call the ground? The ground is the zero, like, it's It's the be all to end all of voltage potential. You cannot get any lower voltage.
Wait,
And
hold
the
on,
trick is
Rick,
though,
are
like
you
in the
talking about the
perception,
surface?
Okay,
Like
so
the Earth? Or like,
yeah, that's
You're just
my
saying
mean
wrong
ground?
stuff.
no, ground is like it's both the surface of the Earth and also the electrical value of it. As soon as you stick a stake in the ground,
No,
right,
no.
that is your ultimate potential of voltage,
no, but okay,
like your lowest potential.
but the surface of the Earth can be my garden at the moment. Surface of it can the road outside. Okay, that's what I mean when you say surface of the Earth. I do not understand it. At one point, you always have this differential or differential between what you are now and slightly higher above. Okay, but at
Yeah.
what point do you say the ground? You see, do you go the
I don't
ground?
understand what you mean, man. Like if I put a stake in the ground and I earth my electrical equipment to that stake, that is the most that's the most zero that you can get to neutral that we can refer to in this natural world. There is no
you want me to
other
explain it?
place that you can go.
Sure, go ahead.
Your understanding is completely wrong about this. Okay.
Who you? Okay, Radio, go ahead.
Wait, explain.
All right, so
you can't just say that. You got to talk
let me give
about
you
it.
let me give you a simple analogy. All right. Let me give you a simple
He's gonna give us
way
a
of looking at
comparison.
this. All right. So let's say, for instance, you've got a battery, and your battery has the positive terminal connected to a plate. Okay, let's say doesn't matter how big the plate is, but you've got a positive.
Sid, I can follow you. Just get through it really quickly. I can follow you really quickly, and we can
then the bottom, and then the bottom one, and then the negative terminal connected to another plate. Okay, now because it's connected to a negative, it's mostly negative. This plate, okay, it will have a propensity of mostly electrons that are trying to get to the other plate.
Okay.
Okay. The difference between those two plates, that's voltage. That's the potential difference. Okay. So there's charges up there. Just because there's charges up there doesn't mean that they're moving down. Okay. In other words, it's charged. It's highly charged. Yes. So in other words, we got ions in the atmosphere that are charged, let's say positively charged, okay? Ions in it, okay? Positively charged ions in the atmosphere, and then lower down we've got the ground, which is negative. So what happens is, unless something actually makes this connection between them, and lightning does, it's going to stay like that. It's not like there's some electricity moving between these two. There's just a bunch of atoms that are
quick question for you.
Yeah.
What restricts the flow of electricity?
Well, there's some sort of for electricity. There has to be a pathway for
insulation. Insulation,
of course.
Right?
Yeah.
Insulation restricts, so that can be a gap, like a certain sort of material. But always, it doesn't matter. Like even if you've got an like a battery just sitting on the side there, it will slowly discharge. Why is it discharging? Because there's despite the fact that the terminals are on opposite side of the battery, there is a slow discharge between the two. Everything is trying to come to an equilibrium.
It doesn't
like your air gap
doesn't.
It does. Yes, it does.
No, it doesn't discharge because
your air
because the air has
it's not
ions.
an absolute resistor of voltage potential.
We got to let Phil. Hey, Rick, we got to let Phil get in. You're kind of like stomping over everybody.
The air, all the air around you has some of the molecules of air around you is positively charged or negatively charged. In other words, ions had got away from it. For instance, a chlorine atom around you might have collected an electron. That's why it's chlorine gas. Or something else might have given away an electron. For instance, an ozone molecule will be charged. These are called ions. So like molecules that kind of stripped off one of their electrons or two of their electrons, just going around in the air, just part of the air. These are called ions. Okay? So generally speaking, so when we say that there's a potential difference in a particular part of the air, for instance, a particular cloud might be positively charged. In other words, it's got more ions that are positive in that part of it, and another cloud might have less, either less positively charged or negatively charged ions. Now, those that between that, so what we say is between the top, the one that's got the positive and the one that's got a negative, we call that potential difference. Now,
Yes.
there still has to be a pathway for them to actually discharge, and lightning does that.
It does it violently. It does do it violently.
Pathway.
Agreed.
Yeah, of course.
Yeah.
It creates this pathway. All right. Once
But
there's a pathway, once it finds a pathway, then yeah, all the electrons will go like mad down that pathway. Once they find a pathway, and then it'll get discharged. You know, when you put your hand sometimes along the you're walking towards the supermarket, you're going up the escalator, and then you get a shock.
Yeah.
Okay, that's because all the rubbing that's going on this escalator is causing static electricity, and then when you put your hand there, you discharge it.
Voltage, not amps.
When's the last time you got an electrical shock from an escalator? I would have thought, like, as far as like a courtesy of going to some. Really?
Yeah,
I feel like
I've got an electric shock from that problem. Escalator many times.
What, you got an escalator at home or something?
Professor Phil, when you're saying negative, you're not saying like actual negative. You're saying just lower charge than the one you're comparing it to.
Yeah. It can be lower charge. It can be negative, or it can just be a lower charge. Yes,
well,
exactly.
When you say negative charge, what does that mean? That's what I'm trying to hone in on here.
Okay. All right. Let's say, for instance, that's a good question. Okay. Let's say, for instance, I've got a neutral oxygen atom. Okay. Now, an oxygen atom, its mission in life, it's got six electrons. Okay. Right. 8 electrons. Its mission in life is it six electrons? 8 electrons. Yeah, 8 electrons. Its mission in life is to get 10 electrons. It's trying to be like a noble gas. In other words, to complete all of its possible electrons. It has a maximum of 8 that's possible. All right. It's only got it's a max of 10. It's only got 8. It's going to do everything it can in its power to get those 2. It's going to get it from somewhere. Now, if it happens to get those 2 electrons, so it now becomes an ion, an oxygen ion. It's now oxygen with 2 more electrons than nature actually gave it. Okay. Now that's an oxygen ion. That's a negative ion. And the same thing happens if we've got some dust, or we've got let's say, for instance, some calcium ions that are around. Calcium also, its mission in life is to get rid of 2 electrons. That's what its mission in life is to do. Well, it's going to do that. As soon as it's possible for it to do that, it'll give away those 2, it'll get rid of those 2 electrons, and then it becomes positively charged. So now you've got a bunch of positively charged ions that are floating around. You've got a bunch of negatively charged ions that are floating around. Now, if they are not together, if they're not floating together, then there's a potential difference between that area where those positive ones are and this area where the negative ones are. Now, if by chance this is a rain or whatever,
this is a romantic story.
Pathway. If there's a pathway between those 2, then what's going to happen is that you'll end up getting a violent discharge. Okay, those 2 there'll be a pathway so that so that the negative ones will float to the positive ones.
Well, maybe I'm stupid, but it doesn't sound like there's true negative. There's just like some kind of circumstance that encourages an exchange.
Yeah, negative just means having more electrons than nature otherwise gave you.
So,
Well, it's
but
potential.
do you realize that like to say negative implies like a type of framing that isn't even really true? It's just a title.
Yes, it's true.
Well, like if I say -5, that
Negative
people
literally means having more electrons than you otherwise would have. That's literally what it
but
means.
just follow me. Just follow me real quick. You're saying negative means it has more stuff. Okay, what I'm trying to emphasize is
Electrons,
that
yes.
okay, fine, whatever. In reality, if I am negative something, I have a debt. I have a balance that I need to pay towards. Now, in
Yep.
this sense, you're
That's a good
saying
way
that
to put it.
negative means negative means it has more stuff, which is not really what negative means. So it's like misusing the term to kind of confuse people.
No, do you understand this concept of ions, right? As I explained to you.
Look, I understand it's a convention. I'm just pointing out that the convention is taking advantage of people who are, in a very cursory way, would interpret negative as not having, whereas in this convention, negative means having more.
When we're talking about electricity, electricity is literally the movement of electrons, okay? Between one place and another. That's literally what it is.
Could you just like respond to what I'm saying? Maybe.
Yeah, look, you're kind of right. There is an imbalance.
Okay, thank you.
There's an imbalance between that. Yes, you're right. I'm not disputing that. There is an imbalance between the amount of positive region and a negative region. I agree with that.
I guess Riggs, what you're saying is, correct me if I'm wrong, okay, but I understand what you're saying. Yes, you are right. It's not negative per se. We say the difference between what is always measured between the difference between two. So you got a higher surface and lower surface. So you got higher and lower. It's not necessarily negative. It's just the difference between them is always less. In this context, we might say use the negative word, but it's not actually minus 100 volt. If that makes sense. That's what you're saying, correct? Which is correct. It's not necessarily.
Yeah.
It's a relative measurement, basically.
Yeah, there's an imbalance between yes, there's an imbalance between positive ions and negative ions. Generally, that's what you would cause. That's what you'd cause a potential difference. That's why we have a potential difference between.
Well, the reason I pointed out, I'm sorry, Pazza. The reason I pointed out though is that at no point are we operating in negatives or even really understanding what neutral is. We're operating in positives. We're just giving the title of neutral negative for the sake of
neutral just means that there's a balance between the positive and negative. Okay.
I mean, there's a different etymology here. There's a different, the word negative and positive is used in lots of different ways. Yeah. I mean, if you want to frame it in a grammatical context as an analogy, you could say I have a negative overdraft because I have more debts. That's one way of looking at how you frame that.
But we are talking about electricity, so we're talking about electrons, okay?
Sure.
Okay.
I do agree. It can be misunderstood. I would say I have negative energy and I have negative volt. People go, it does this mean it's minus 10, minus 100, minus 50. So there's a bit of a can be misunderstood. Sorry. So Pazza, your example was quite nice actually. Minus 200, but it means I have more depth. Okay.
I could explain it in correlation to like a lattice in chemistry, or I can not because I'm You see, I was ready. I was like, or I can not. Like,
I guess it's just important that I point something like that out because, like, if the convention is imposing a perspective that gives the user like the wrong, like, it's almost intentionally confusing, is what I'm trying to say. Like, it would be totally fine to operate within positives. There's no problem with that. But then
this is
to denote neutral and then after the fact invoke negative. That's That's like intentional gaslighting. I would call it.
Well, I mean, this happens all the time. When you first learn electronics, you like say you learn about positive, negative. You're not dealing about, you have to learn to, you have to appreciate the words in the context of electronics are contextually, completely different to how you use them in everyday language. That is true.
Yeah,
You're right.
But what it's doing is it's invoking that negative is relative, which is just another way to like like you have relativity on one side, with Einstein and all this, and they've pushed this paradigm of like moving, like basically moving frameworks, right? Like depending on your reference. And so now they're just using the same convention in electronics, not because it's necessary, because it suits a narrative that everything's relative.
They could have used they could use any other alternative words or made up words. Yeah, I mean, when you're working in electronics, positive and negative means one thing. When you're dealing, for example, in life experiences, general everyday life experiences, positive and negative mean something. When you're talking to someone on the radio and they say negative, they mean no. I mean, the word gets used in different contexts, in different places. This is just the way we use words in English, isn't it?
I would say that it is distinctly different in electronics. That it's well, I guess I'm trying to bridge the gap here. I'm trying to make it obvious that it doesn't serve any actual function in this jargon. It's literally just gaslighting to normalize a relative construct.
I mean, no one in electronics has got a problem with this, and no one sees it as gaslighting. It means something in electronics. It means something everywhere else. I mean, the fact that they're describing an attribute of something as being negative by virtue of the fact it has electrons. The electrons have got a negative charge. It's the convention they've used. They could have called it something completely different, but they've given it a polarity essentially. Yeah.
Yeah, I agree.
And then in that context, they can use mathematical and equation constructs to manipulate the concepts. But it doesn't really make much difference. It doesn't actually. Most people in the world, talk about electricity, have misconception about what it is or don't understand it at all. They just switch things on, and that's all they really got to worry about.
Oh boy. Sorry,
it's true, isn't it?
I get really triggered when people say don't understand, because this is like literally the only thing that Omnivore says.
Well, I mean, most people haven't got a really, really good grasp of electronics, have they? I mean, it's just the way the world is. Most people,
I don't claim to understand electronics.
Sure, but then to say, well, that the fact they use words slightly differently in a different convention in some sort of discipline or niche thing is gaslighting. I mean, it's not. If it's not in the common vernacular of the common man, it's not really problematic, is it?
Yeah, you can have 80 million different, too many choices of too many ignorant people saying too many different ignorant things, and then you can poison the well. And this is where we are right now. Because you guys think
Can I say something?
No, but you don't.
Let me explain something.
Thank you, Gemma. Go ahead,
Can I
Phil.
explain something to you guys? Okay. All right. Yeah. You guys know about this copper sulfate. It's a beautiful blue color. You heard of that, copper sulfate?
Yeah.
It's used for killing algae and all stuff like that. Okay, so beautiful blue color.
It's a classic electrolysis demonstrator, isn't it?
Aha. We're on the same page. Yes, I'm just about to explain that. Exactly right. I'm just about to talk about that. All right. So what happens is we've got so this blue stuff. When it's dissolved, you've got copper ions, copper 2+ ions, and you've got sulfate ions. That's why it's called copper sulfate. So it's dissolved. So sulfate ions are floating around. Copper ions are floating around. Copper ions are positive. 2 positive charges, in fact. All right, they're missing 2 electrons. Now, if they could just get 2 electrons from somewhere, they would turn into copper, into actual copper metal. All right, that copper 2 ions would turn into copper metal. If they could only get 2 electrons from somewhere. Well, if we put an electrode in that copper, what will happen is that electrode will start to disintegrate. Let's say it's zinc. That zinc electrode will disintegrate. itself, it'll be like it's getting rusty in terms of zinc, right? Zinc doesn't actually get rusty like brown stuff, but it does oxidize. Now, when zinc oxidizes, you know what that actually means? Zinc gives away those 2 electrons, and copper says, thank you very much, and turns into copper. As the zinc erodes, the copper sulfate starts getting lighter and lighter in color. That's because each one of those copper ions is now turning into copper metal. But the zinc is paying for it. The zinc now is getting eroded. This is why we have sacrificial anodes in water systems in that. And that is because instead of the walls of the container getting eroded, what happens is we allow the sacrificial anode to get eroded, right? So that gets eroded. It could be a bit of zinc they put a lump of zinc in the water system, and the zinc gets eroded. It doesn't erode the other things in your water system. Okay, so when something gives away its electrons, something is ready to get it. If there is a pathway to it, if there's no pathway, then these charges are going to build up and build up and build up like they do in the atmosphere, build up, and then finally, it could be raindrops or something like that gives them a pathway, and bang, lightning. Okay, so lightning is just a movement of billions and trillions of electrons at the same time.
Capacitance.
Yeah, well, a capacitor is an exact thing like that. What's a capacitor? A capacitor is two plates that are negatively and positively charged, standing away from each other. In other words, they highly negative and highly positively charged, and they've got a piece of paper in between them. This that can't conduct electricity. So now what happens is you connect your capacitor to a battery or to some source of electricity, and you charge that capacitor up. In other words, it takes on electrons. Okay, it has the potential to take on electrons, and as it does, it's getting kind of like filling it up, and then when you connect it to a load, then those electrons are going to move from this side of the plate of the capacitor to that side of the capacitor, and there you got it. A movement of electrons. What do you do with the movement of electrons? I don't know. Make a LED light turn on.
Well, could I ask a question to you for the flat earthers?
Yeah.
Oh boy.
Could this phenomenon of electricity that you've studied ever make things fall towards a flat earth, like rocks, humans, rain?
No, static electricity is pretty strong, but it can't make things. It can superficially make. It can make very light things move, like paper and molecules that are really, really light that are moving around. But
no, I'm saying, Phil, if Earth is flat and magic, could electricity do that?
No.
Okay.
No, it wouldn't.
Have you ever, Dr. Phil, have you ever heard of the concept that there are 8 different types of electricity?
No, electricity is just a simple flow of electrons. Okay, that's all it is. Nothing magical about it. You know, people think that they think electricity moves.
Have you ever heard of it?
Did you know
I have trouble getting a response from you sometimes.
Did you know that electricity doesn't flow through wires?
I understand that. Yeah, you can use an ohm clamp. I understand. Look, I'm asking you to engage with my question. Have you ever heard of there being 8 different types of electricity?
No, I just know about electrons. That's it. That's electricity. That's the movement of electricity. There's static electricity, of course, which means it's static. And then there's Yeah, and there's current electricity, which is
I'm
moving.
just trying to I guess point out the idea that there are some people who have, you know, they've historically thought that we operate in an etheric world, and they observe 8 different types of electricity, which is what they would call like different expressions of this background medium, which produces this electrical phenomena that we're even speaking about. So I just wondered if you heard about that.
No, I haven't. And when anyone says electrical to me, I immediately think about electrons.
Okay.
Mm-hmm.
Yeah, that's
literally,
okay.
That's what it means. Electrons moving from here to there, finding a pathway to move. There you have electricity will go.
Millions of people buy butt plugs every day. So what do you think? So you can define like kind of how we engineer electricity right now with like AC and DC, right? So AC is cycles. So you can have various cycles, you know, high, low, whatever. And then you can
You
have
get a slip. You got a slip ring commutator, okay? That produces AC. There's DC is produced by a split ring commutator, and AC is produced by a slip ring commutator. So basically, electrons that move backwards and forwards at 50 times per second in Australia. I think in America, it's 60 times a second.
So how do we explain a current that moves in pulses or non-sine wave patterns?
Okay, so basically the electricity generally moves in sine waves, but you can cut them off. So in other words, you can square off a sine wave. So if it's AC, I'm talking about, okay, you can square it off. But for DC, you'd smooth it. So in other words, you'd make sure that there's no return path. So it's never going to be negative. So sine wave is positive for a certain part of it for half a period, and then negative for the other half of the period. Okay. So what DC current is, instead of having the negative half a period, that becomes 2 bumps, which are the first bump is the half a period, then the positive bump is the second half a period. So DC always stays positive. But AC goes half a period, the bump for half a period, and then goes the other way, producing a negative, then a positive, a negative, a positive, a negative, and so on. So that's AC, all right? That's alternating current. So this direct current just means that there's just bumps. Now, if you've got a computer or something like that, you don't want those bumps. You want that to be smooth. So then you introduce a capacitor. So capacitor gets charged up, and your computer actually uses the electricity from the capacitor, because capacitor can deliver that charge very smoothly. Whereas if let's say for instance you buy a cheap charger. Don't buy cheap chargers, all right? That's not good for your equipment. And that is because they don't bother to put a capacitor there. So you're just having the raw DC current. The raw DC current is bumpy, okay?
Yeah, it smooths it out. It conditions the flow. Yeah.
So if you go and buy a real Apple one, Apple spends a lot of money to make sure that the voltage from there is smooth as can be. If you go and buy a cheap one, chances are it won't even have a capacitor.
Interesting. Have you seen how they've explained like the resistance on a wire to current flow?
Resistance just simply is something that blocks the path of electrons. So it ordinarily, without any, with no resistance at all. For instance, a nice big thick piece of copper wire. you know, that electrons can travel on the outside of the wire. Of course, that's why it's shiny. By the way, metals are shiny because of the electrons that are on the outside of it, not the inside. And so electrons are. So a resistance just means some way of stopping those electrons or reducing the ability of electrons to go from here to here. Okay, along a wire. And that might, like a really poor quality wire will have more resistance, because a really good wire will allow all the electrons to flow unimpeded, completely unimpeded. Whereas a poor quality wire will have won't be able to have that many electrons. Just like a thin wire. Let's say, for instance, a 1 millimeter wire, which we use for lighting, that's 1 square millimeter that the wire is. Well, a 1 millimeter wire can only take so many electrons on that's outside of it, because electrons move on the outside of the wire, not the inside of the wire. So it can only take so many. But now, if you've got a PowerPoint wire that's going to, for a heater, that's 2.54 square millimeters. So because that's bigger, a lot more electrons can move along that wire. That's why you need thicker and thicker wire if you want more and more current.
Have you seen how they solve for how hysteresis solutions have come to the modern application, where they change the waveform to exactly match the distance between transformers?
Yeah. Okay. So what you're trying to do with transformers? Transformers are actually an amazing piece of stuff invented by Faraday. And basically what happens is you've basically got two coils, right? A primary coil and a secondary coil. So a primary coil, you put electricity in the primary coil, and if you put electricity in a coil, you create a magnetic field. Okay. Now, a moving magnetic field. So you put electricity in one side of the transformer, and then you wrap a coil on the other side of the transformer. Now, what happens is the magnetic field, because it's AC, goes backwards, forwards. And guess what happens when you have a moving magnetic field? It creates an electric field. So on the other side of the transformer, you now have electricity flowing. Okay. And the beautiful thing about that is you can really predict. So let's say, for instance, we've got 100 volts on this side going through 100 turns, and we've only got 10 turns on the other side. It's going to be 100 volts here and 10 volts over there. So you can step down the transformer from 100 volts down to 10 volts just by simply having 10 turns, 10 turns of the wire instead of 100. So it's 100 turns over here, say 100 volts, 10 turns over there, and now have a step down transformer. Or we can do it the other way. If you come in with 10 turns, let's say you come in with 10 turns with 10 volts, you can actually step that up. It'll cost you, right? But you can actually step that up to 100 volts. So so that's a step up transformer. We see them around in the suburbs, both step up down and step up transformers.
Yeah, just to help clarify, could you explain how the wrappings?
Yeah, so basically, okay, this is how it was discovered, right? So Faraday had a cardboard tube. That's all he had, cardboard tube. And what he did was he wrapped some copper wire around it. Okay, so quite a few coils of copper wire. He wrapped it around this cardboard tube, and then he connected that cardboard, the two ends of that wire to an ammeter, right? And what happened was he then dropped a magnet down the tube and created electricity. And suddenly that ammeter moved. And he goes, "What?" That floored everybody, because you haven't connected it to anything. You just dropped the magnet down the tube in between a coil and wire, and it created electricity. That's all it is. So now you're saying, well, all the engineers, once they saw that, like Tesla, for instance, he's the main guy who did that. Once Tesla saw that, and he goes, shit, I can make some money out of that. Because if you can imagine, if you could keep throwing a magnet down a coil, you're making electricity. But how are you going to keep that magnet going down that coil? Well, Tesla thought, why should the magnet move? Why don't make the coil move? So that's what Tesla said. Tesla thought, make the magnet stay still and make the coil move. And that's what he did. So he put a whole bunch of magnets in a circle, and then created a coil in the center that turns. And now we have generated electricity. It was so simple, and yet there's a genius. See, so now he's created an electric generator. Still use it today. Exactly the same principle.
Genius needs space to breathe.
Okay. A moving electric field creates a magnetic field. A moving magnetic field creates an electric field. That's why the core of the Earth isn't magnetic. All it is two things moving past each other, and because they move past each other, they create current eddies. They create electrical eddies. Now, this is a moving electric field. What happens to a moving electric field? Creates a magnetic
basically,
field.
you're saying that the Earth isn't a rare Earth magnet. It's not a lodestone. It's the magnetic field is being generated by a flowing electrical current.
Bingo. Yes, absolutely.
Yes.
The American.
Thank you.
Yes.
Thank you. That's what I've been telling people.
That's exactly right. It's not some sort of magnetic thing. It's hot stuff moving past the other, and because they're moving,
it's going to be uneven in its distribution because it's going along a path. No different than like how a lightning strike takes an irregular path towards its arc point.
Yeah, it's totally uneven, and that's why when we measure the Earth's magnetic field, it's not even. It varies here and varies there and moves it. Generally speaking, the magnetic field moves from somewhere in the Southern Ocean and finishes up in Canada somewhere. Generally speaking, that's its direction. But it actually goes in many different directions and is swirling around. It's never ever static. That's why magnetic. That's why we have to make the needles on compasses actually make them magnetic. Okay, because otherwise they'd just be everywhere. And now, of course, we don't use compasses like that. Now we rely on gyro compasses, so that we don't have to rely on magnetic compasses, which are notoriously unreliable because it's not always the magnetic field's not always constant on the Earth because these eddies are not, this electric field that's being created by the movement of these two things past of each other are not constant. Like you said, you quite rightly said, they're all over the place.
Yeah, it's literally like a scaled up version of, like you said, you move the wrappings, not the magnet.
That's right.
Yeah, that's really interesting.
You can imagine now you had Tesla who came up with this idea of actually creating just, if you can only get that armature, that coil to move. So what do? You get steam to move it. You get a steam turbine moves that armature past those magnets, creating the field. And Edison, the American guy, Thomas Alva Edison, by then he had worked out the DC current. So he'd worked out how to make electricity DC with it. And of course, Tesla was going to win hands down. He couldn't fail because he could send electricity over long, long, long distances. He had the step-up transformers, step-down transformers. He could make electricity go for 300, 500,000 kilometers. Edison, he could only make he could hardly make a mile. He could hardly go he'd need a generator about every mile away. You'd need another power generator if you were going to run DC current. It was that bad. So there was this big fight between Edison and Tesla. And of course, what happened to Tesla? Unfortunately, he was a great engineer, but he was really a shithouse businessman. And unfortunately, he got tricked and all that. And Westinghouse is the guy who actually took Tesla's work and turned it into that. Westinghouse and General Electric. There's two companies that ended up stealing that, and now they biggest companies in the world.
I'd like to.
Unfortunately, Tesla died poor. Would you believe that? After all that, he died poor.
Yeah, a lot of people know that. That's really wild. I wanted to ask you because this is, dude, I love your knowledge. So
yeah,
since you're a fan of Tesla, I wanted to share this little insight I found from William Lin's book. He said that Tesla agreed with a mechanical view, and this is kind of stating that we cannot call electricity the ether itself. But we can definitely say that the so-called static charge of a molecule is simply bound ether that has become associated with the molecule.
Look, who knows? Who knows? I don't know. Maybe what I know, because my background, my initial background is in chemistry, so I did a lot of work in chemistry, and I do understand this concept of redox, of reduction, oxidation happening in chemical reactions, and I know that's the passing of electrons between this substance and that substance. That passing of electrons, if you've got a way to capture those electrons while they're going from here to there, you can actually get them to do some work, right? So I understand that concept. The thing about it is that all atoms that are not noble gases are the lucky ones. They cannot give away any electrons, and they can't accept any either. They are those are that's why they call them noble gases, right? They can't react with anything. All right. So, but everything else wants to be like a noble gas. That's its mission in life. So either it's going to give away one electron, two or three, in order to get there, to become like a noble gas, or it's going to take some electrons in order. So oxygen takes them. Oxygen actually takes electrons in order to be like a noble gas. Okay, and where's it going to take from? It's got to take it from somewhere. So whenever there's a negative ion over here, there's a positive one somewhere else that matches it exactly. Okay, so it's when these two actually finally come together. There's a pathway between those two that comes together. It could be rain, could be mist, could be fog, anything like that. Once they have a pathway, then those electrons are going to go where they belong, and those ions are going to get the electrons that they desperately want. And once they get those electrons, they get it in a very violent way. Okay, and we call that lightning.
I got a question now about
plasma.
chemistry.
It's not lightning; it's plasma.
So if I call the anions.
Plasma means no strip of electrons. That's all plasma means. Okay. Yes, the effect is a plasma. Yes, correct.
So Phil, if I call the anions like the scaffolding, right? And I call the cations like the hole fillers.
The anions. Yeah.
Yeah. Okay. Yeah.
Yeah.
And
So
then
anions. Anions are negatively charged ions. Okay. Cations are positively charged ions.
Yeah. So what if I said
that? The copper. Okay. So the copper 2+ are cations. Okay.
Yeah. So what if I said the cations, like these? This is the empty space in between the anions. What if I claimed that that's actually just electrostatic charge in equilibrium?
Oh no, because I mean that's electrons are things that have mass. You know, I mean they're not. They think we can measure them and detect them and all that sort of jazz. These electrons, by comparison to things like light, are very, very heavy. Okay, they're huge. Electrons are huge compared to photons like light. Okay, so if there was some sort of thing in between, it has to be even smaller than light, even smaller than photons. They have to be much, much smaller than photons. Okay, so we don't know, we can't measure anything that's smaller than a photon, right? We just got no way of measuring. We got no way of even detecting anything smaller than a photon. Photons are it, as far as we can tell.
No, we do measure, like, a virus is smaller than a photon.
No, definitely not. The photon's got no, virus have got a mass. Okay? Right, they got mass. Things that got mass are much bigger than photons are really, really, really so small that they're pretty much massless. Okay?
Well, we can see the empty spaces.
You say pretty much, I say they are, ipso facto, they're massless.
We can see the scaffolding of the anions, guys. Like, that's why I'm positioning this. We can see this physical scaffolding, and we can see the empty spaces. Okay? So I'm kind of I'm testing you a little bit, Phil. These empty spaces, when I claim that they're electrostatics in equilibrium, and you're going off about particle science, it worries me.
Why?
Because you know what the structure of these lattices are. You know that there's empty spaces in between the anions. And you're saying yourself, we can't measure particles these small. Yes, these are groups of much smaller charge relationships.
Anions are just negatively charged ions are called anions.
Not a particle. It's a space.
No, it's not. It's a particle. You have
when an atom loses an electron, become a positively charged cation, it drastically shrinks in size.
No,
like these spaces are there, and we can measure them with the contrast and the lattice changes. Yeah, we can.
A thing becomes a cation because it's lost electrons.
In your battery comparison earlier, right? Sacrificial, non-sacrificial anode cathodes, we have the same exact examples. We can look at the lattice structures. We can look at the shrinking in size as a result.
No, what happens is they become part of the solution. So as copper sulfate, copper ions
in an aqueous solution, but in a non-aqueous organic solution, you have the lattice survives.
It's pretty much the same. It's just the same thing, but just a lot slower. Okay, because the air is actually a fluid, right? It just happens a lot slower. That's all. In solutions, it happens really quickly.
Yeah, but that would be an aqueous solution. You can still have like an organic solution, like some of the meta batteries.
There's no electricity. Electricity doesn't move in. Electricity can't move in organic solutions.
I'm just presenting to you there's different dimensions of chemical reaction that can occur in these batteries, like lithium ion. You can probably explain that. Why is it non-sacrificial?
That's not that. So lithium ions. Listen to what you say. You're calling it lithium ions. All right. Okay. So what happens is you've got lithium ions, right? Why do we call it lithium ions? Because the lithium is missing. It's one electron. Lithium is satisfied by one electron. Okay. All right, it's missing that one. If we can find a way for something else to give away an electron and give it to the lithium, okay, or where lithium has its lithium metal, and its propensity is to lose an electron. If we can get that electron to move from here to there, because it desperately wants to do that, then we can use that electron. That's a battery. A battery. And how do we know this? You know, Einstein.
Well, they're shuttled between these lattices through the medium, be it aqueous in a sacrificial, and organic non-aqueous solution.
No, it's not organic. No, organic stuff can't turn up electricity. Electricity can't move through organic stuff.
Physically shuttle between distinct inorganic without destroying the overarching crystal architecture. So this is a non-sacrificial relationship, and they're already looking for even closer. Let's see.
There are no organics. There's no organic. There's no
called
organic
a Parback's diagram. Have you ever seen this? This shows
organic means carbonation,
where you begin
right?
to convert water. You begin to convert the solution versus where you sacrifice the material versus where you get
these are inorganic
electrons. I'm trying to connect it back to the empty spaces in the lattices, right? We can see those shrink depending on the different battery technologies. And these aren't a full concept of what we're talking about. These are just examples, right? So we can say there's a sacrificial anode, non-sacrificial, but that's one type of
do you understand what it means by sacrificial anode? Do you know what that means?
Yes,
it means like zinc. Zinc will give up 2 electrons and become part of the solution. So as the copper is taken up, as the copper reduces back to copper metal, each one of those, zinc, for every molecule, for every atom of copper that's made at the cathode, the anode will give up an electron as well. So 2 electrons get taken up by the copper at the cathode. 2 electrons get given away by the zinc. So eventually zinc giving away its electrons like that, it now becomes part of the solution. It gets corroded. This is why we use zinc as a sacrificial anode, because it easily gives away its electrons. Okay, zinc gives away its electrons easily, so that's why we use it as a sacrifice. So it gives away electrons and it's picked up by something else. And instead of the walls of the container getting eaten away, or the blade of your speedboat propeller getting eaten away, the zinc gets eaten away. Okay, the zinc loses its electron. We don't want the walls of the container to lose its electrons, so we say the zinc is much, much more likely to lose its electron. If there's a cation, there has to be a matching anion.
Yeah, I'm trying to show I was just asking my question around these empty spaces in between.
I don't know anything about that space, empty spaces. Okay, I don't.
That's what I'm wondering, because like you can see it in your models, like all the textbooks you use to learn about chemistry. You can see
I write
and coordinates and how to map those.
I've never written anything. Are you
playing dumb because you think I'm leading you off? I'm really asking. I'm just trying to ask.
Okay, I've never written about spaces, and I've written many, many textbooks. Okay.
Okay. Do you know what a cation and an anion is in the structure of a lattice?
Of course. Of course I do. It's my wheelhouse.
That's what I'm wondering. Am I speaking the wrong language?
No, I just don't know. I don't know what you mean by spaces and stuff like that. Okay. All right. So the lattice, metallic lattice is basically electrons that are on the outside. So electrons tend to hover around the outside of the lattice, and then the cations make up the bulk of the metal. Like electrons are very, very tiny and very, very small, but the bulk of the metal is made out of cations. Okay, so positive ions. That's most of it. The electrons that go around the outside of it, while there's lots of them, they don't actually make up the metal. They make the thing shiny. They're the things that make metals shiny. Okay, that's why we look at that's luster. Luster in a metal is because of the electrons on the outside of it. Okay.
That's actually a really good
I don't know anything
point.
about spaces that you were
That's a
talking
really
about.
good
That's
point
not-
because you can determine something's conductivity by like how reflective you can make it. That's what I heard.
yeah. The more reflective, the more electrons there are there. Yeah,
Yeah,
exactly.
isn't that wild?
Yeah, it is. It is, and like, that's why electricity doesn't flow through the metal. It does inside the metal. It doesn't. It flows on the outside of the metal. So when you've got a wire, the thicker the wire, that means there's more surface area for the electrons to flow. Therefore, it can carry bigger current. The thinner wire, not so much surface area, so it can't carry. What's going to happen? That's going to get hot.
So
As
so
you try to force.
if you have a cable with many fine strands of line,
The
you
best.
can
Yeah, more surface area.
if you group them together. Yeah, that's
exactly.
cool.
So if you're going to go and buy some cable, and you see one thick cable and another one with strands are better. You pay more for it, but electricity, you have less resistance in that cable, and you'll save more electricity if you use the stranded cable. More surface area. That's what you want. Anyway, this is my first night back after coming back from hospital. I'm going to have something to eat, so I'll listen to you guys talk, and I'll come back in a bit.
Yeah, you sound good, Phil. I'm glad to hear you're back from hospital. Welcome back.
Thanks. I really appreciate that. My life was really on the line. Seriously, it was touch and go, and I've pretty much beaten this cancer, so I'm good to go for a while. Just got to get this past the surgery. So thanks for that. I appreciate your thoughts.
Yeah, no problem. Yeah, it's Riggs, by the way. I change my name every day, but just call me Riggs.
Riggs, yeah, I see you around a lot. So thanks very much for your thoughts. Some people have wished I died, but there you go. I'm glad you're not one of them, Riggs. Thank you.
Yeah, I find that pretty disgusting. I hope nobody wishes that on anybody. Yeah, I find that pretty interesting, Tank, that a lot of the answers we're looking for exist between the particles. You know, those relationships.
Yeah. The in-between seems to be up to something they can't quite explain. And the more that they're pushing the edge of these modern batteries, where they're able to push into the non-sacrificial anode-cathode relationships, I mean, this is pretty much evidence that they're starting to just start to see these other dimensions of motion. And this is the electrophysics comes into play here. Like, obviously, like, it's crazy.
Well, they just can't explain everything with the particles alone. So then you have to start looking at the other space.
Yeah. Measuring boundaries at 0.77 volts in chemistry. Like, this stuff is wild. It's making me think of Terrence Howard. Like, maybe he was stepping into some stuff he wasn't allowed to talk about quite yet. The spaces in between.
Yeah, Terrence Howard, you know, he was cooking a little bit, but the guy he was sourcing from for most of his stuff, I think that guy was more on point. I forgot that guy's name. He had all basically like the wavelengths on the periodic table. You probably know his name.
Oh, Walter Russell?
Yeah, Walter Russell. Yeah. I think that guy was mostly spot on with some of the ideas that he had.
Yeah, and Phil went into some really cool information talking about the periodic table. He's talking about how all these other things want to give up their electrons. That's some powerful knowledge. That correlates with a lot of Walter Russell's work in his harmonic nodes.
Have you gone to bed yet, or you been up this whole time?
I slept for like 3 hours. Woke back up.
Oh, okay. Yeah, I slept like 3 or 4 hours too.
Screwed. Like, well, I'm awake.
You know, I just remember at the beginning of Flat Earth, I almost never went to bed. I was just, you know, absorbing, because like, and not just Flat Earth content, like you're taking in concepts and just like researching them, you know. And because of that, there was just such an awakening. I spent all my time just like digging, trying to find more information.
Stoking the fire. The bellows are pushing. Yeah, it's when an atom loses an electron to become a positively charged cation, it drastically shrinks in size. So this is these little spaces, since a much smaller equilibrium of electrostatic charges is available after this new charge takes up that spot. You have even smaller. You get a shrinking. Like it's not the object changing size. There's one little electron leaving and changing the equilibrium of charge balance inside the lattice.
Technically speaking, an atom would get smaller if it lost some electrons, but electrons are really, 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 really tiny. So it would be completely insignificant. We're actually, when we're actually looking at the atomic mass of atoms, we don't even consider the electrons. They're so small. We don't take them in. We only take protons and neutrons into account when we looking at the atomic mass of and weighing an atom. If we consider the mass of an atom, we're only considering the protons and neutrons. Electrons are practically nothing. Electrons are so small, they even have a wavelength as they move, like photons.
Have you ever heard the term used like atmosphere for the charge barrier?
Yeah, so as I was saying before, you've got the air, which is, you know, we say it's about 100 volts per meter. The potential difference is about 100 volts per meter as you go. But mind you, it gets less and less. So it 100 volts per meter up to about 100 meters, about 10,000 volts, something like that. The potential difference. So there's a lot of ions higher up, but you know it gets less and less as you get further. So it's not a gradient like the air is. You know, it gets less and less. And now nothing's going to happen. It's just a really, really big buildup of ions. You know, ions can be stripped by light, stripped by all sorts of things. So you have a lot of ions, cations that are floating around, if you like, and nothing's going to happen. They just keep building up. And then until the point where that electric field strength is stronger than in other words, it's able to find a path through the atmosphere. So once it finds a path through the atmosphere, bang, it discharges. All of it discharges at once, creates plasma on the way down. There you have light.
What's actually stopping us from using some sort of advanced method of like frequency output to create different charge domains and to technically align light or vibration into matter? What's stopping us?
We can look. So we can. All right. There's two ways. There's two things we can do. All right. So one is that we can use light to to smash into a particular type of plate, so type of metal, and a particular frequency of light. So light at the green frequency, so around about 500 nanohertz. That's about 500 to nanometers. 500 to about 300. 300 is around the blue area. Those are energetic enough to kick off an electron. They can actually, as they shine on a metal plate, they kick off an electron. And what happens is we have a cathode, which is basically a collector that can collect those electrons. So as one photon hits the metal plate, kicks off an electron, that electron's collected. Like a battery, like a capacitor, you just keep collecting them.
So like you said earlier, there's certain. Oh, sorry. Good.
That's how a solar cell works. That's how your solar electricity works. Okay, so solar electricity works. That's why the only useful part of the sun shining on your solar panel, right? And that's why that's best during the day and no clouds scatter the sun, so you don't get much. But the reason is because you want the blue wavelengths and the green wavelengths to hit that. The others, like red, like the red wavelengths, like heat, infrared, they're useless. You don't want your solar panel to heat up. Okay, you want it to stay cool, and you want it to be hit by high speed waves like blue waves or green or purple. These are the really powerful waves.
Reduces efficiency.
Yeah. So the better the metal that can kick that these lights can kick off electrons, the better your solar panel. That's why solar panels are not just solar panels. There's good ones and there's bad ones. The expensive ones are the ones that are made out of metals that will lose an electron really easy. So the light comes in, bang, off goes the electron, gets collected, and that collected electron then becomes part of your, I don't know, you send it to a grid or a battery or whatever you want to do with it. But yeah, and Einstein, by the way, won his Nobel Prize for this very thing called the photoelectric effect. And today we have solar panels, and that's exactly what this is happening.
Well, I asked that because, like, if we ultimately can measure all of these charge barriers with just that, with a charge, what's really stopping us from using our magnetic domain technology that creates frequency outputs to focus that into an environment and be able to eventually engineer charge barriers? I mean, it's purely fictional right now, the amount of power, control, the mathematics behind that. But
when you think about it, right? So we got clouds, we got the 100 volts, just a meter, 10,000 volts, 100 meters up there, and you're thinking, well, you somehow have to get the electrons that are further down up there. That's what you have to do. The air is an insulator. It can't do that. Normally, if it's raining, you've got a good chance that's possible. Or if it's very humid, there's a good chance that there's a pathway for electrons to get up there. So you've got all of these positive charges up there. How can you use it? What could you do? Could you have a plate there that would become positively charged, and then somehow connect that to that? The trouble is, it's not scalable. Okay, so yeah, on a very small scale, it just isn't enough of it. If there was more,
there's one train of thought though that all these electrical like grid lines that we have are actually used to harvest electricity, and then they use a resonator to like amplify it, and it produces like functional electricity that we have. So there's this idea that they're using free energy systems right now, and they're just charging us for it.
Well, it's not free. It's just that it's not something that's not harnessed. That's not easily harnessed. So let's say, for instance, you walk underneath. Let's say you walk underneath a 70,000 volt power line, which you see going, city to city, town to town. You can walk underneath it. You can literally feel the vibration because there's force going on. As electricity passes through a conductor, it creates a force. It actually moves. It actually vibrates. The electricity causes that wire to vibrate. Okay, because there is actually a force. Now you can actually feel that. You walk underneath that. You can say, look, you can kind of feel the electric field because you've got electricity in your body, so you can feel that. Now you're thinking there is an electric field underneath those power lines. What we got to do is we've got to find some way to make a magnetic field move through it. If we can get a magnetic field to move through that electric field, the electricity is passing there whether we like it or not, going from one town to another. Can we use the electric field that's underneath those power lines, or around those power lines, should I say, because they go all around? Can we use the electric field to actually move through a magnetic field? And in which case we can then suck up some power from the fact that that these wires are creating an electric field. That's interesting. So you're pretty young. Chase it up. I'm in my 70s. I haven't got time anymore.
I talked over Ricksky earlier. He had a question. I was going to see if Ricksky remembered his question. He's probably busy working, but I was going to ask him because I talked to him.
What were we chatting about when he brought it up?
Don't you out the current
thing, how we can harness electricity from so the electric companies pay for the electricity to go down those those cables, but and as they go down those cables, they're creating an electric field. And we're thinking, well, wouldn't it be interesting if we could harness the electric field that's already underneath those power lines? You could a lot of it, the electric field there. We could harness that. So okay, harness the. They probably not left you though. They found you doing something underneath the electric field and pinching, using their electric field that they created to benefit you. They might get upset at that, I suppose, because they'll argue that the land underneath the power lines belongs to them. Mind you, it's not just underneath; it's in all directions, of course. So that would be, you'd have to get close enough to the power because the electric field's strength gets less and less the further away you are. So you might want to get within a meter of the power lines. These days, there's so much more they can do, that could be done to make electricity cheaper, but they're not interested in doing that. They're not interested in finding other things and adapting the electric field to that, because they get their money. They want to get their money the quickest and the cheapest way they can, and they're not really interested in creating things that society might benefit from them. They're not that interested. They just know if I make enough electricity, I can sell it and make it the easiest way that they can. But I would be interested in knowing how we can use electric field.
Can we not apply that to the whole field of science in general? Like with this iteration totally. Of the notion 100%. That it's more interested in creating or generating profit than it is truth.
Yeah, because I mean, you just think about all the heat. We got electric. We've got say electric company. You have a look at the towers that are cooling off, right? Okay, and they have tremendous amount of heat that they just dissipating into the atmosphere. They're purposely doing that, and you're thinking that's ridiculous. You just created all of that heat because the electricity, the whole power station might only be about 20% or 25% efficient. So in other words, of all the energy, 75% of it is in heat. Well, for goodness sake, why are you venting this off to the air when you could be using it? Well, they don't care. That's why. Okay, they don't care. They don't want the heat. The heat is they want
So
to vent
I'd
it
be
off.
kind of curious, like Phil. Obviously, a whole bunch of scientists and engineers were involved in the construction of such a infrastructure, and yet what you observe is this like inherent wastage. Is that what you're referring to? So,
totally.
how are the scientists and the engineers all corralled into the notion of this wastage in your interpretation?
Well, really, by the time it gets over there, we're only talking about engineers. So scientists are the people who try and work out how things work, and the engineers work out how they can make money from it. They're just not interested. Okay, that's the unfortunate truth. Right? There's so many processes that are done with so much waste, and they're just not interested. Why should they? They make their money anyway. So we are so behind. We're like the Stone Age, really, compared to where we could be. Okay, to be honest, all right, because all the things we do these days are geared around, how can we use what we're doing to make money for somebody, and very little. A lot of my work through all of my stuff. I have to admit, I've invented a lot of stuff, and just about everything I've ever done has been with a no claims, with a disclaimer. That means I can't even talk about that particular technology. I can't even mention the stuff that I've done because it's owned by the people who commissioned it. Unfortunately, a lot of stuff's like that. It's proprietary stuff. It's owned by the people who paid for the research. That's the unfortunate thing. Nobody. It's some universities get grants and stuff like that, and they do some research, but really, the real bread and butter of research is done by people who are employed by some organization, and then when they discover something, they just have to keep it secret. That's the name of the game. The money's got to come from somewhere, and
what are you guys talking about?
Just talking about science and technology in general, and what you get to use, and what gets and what gets hidden from you.
Are you suggesting that there's something that could replace fossil fuel?
Oh yeah, of course. Yeah, definitely.
What?
Well, all the fossil fuels, we can replace it with all the biofuels. I mean, that's one of the things that I teach, and that's biogas, stuff like that. We could, but the thing about it is that you've got this hill that you've got to climb over, right? It's like anything. Once you're over this hill, everything from then is cheaper. But
hold on. What do you mean biofuels?
Who's willing to pay to climb the hill, though? That's the problem.
What do you mean biofuels? And where would you source them?
Well, all the things, all the kitchens around the place, all the people, everybody who produces carbonaceous materials and byproducts are potential for biofuels. Okay, all we want are looking for things that have the long carbon chains, and there's plenty of it around. Like fatty acids everywhere, but we waste most of it. We bury it. And that's because society is not willing to pay to get over that hill. It's just too easy and it's just too cheap to keep using the fossil fuels. It's no one wants to pay to climb that hill, to get over that hill and say, right, okay, once we're over it, we don't have to use the
dude, hold on, bro. What are you talking about? Grease traps? What are you talking about? Where are you getting the biofuel from?
Well, we use biofuels all the time. Biofuels come from plants, for instance. Okay, from stuff we use. Tree, even anything that we use that's biology and we waste it is a potential biofuel. There's biogas, which is obviously methane, that comes from from bacteria that breaks down anaerobic breakdown of carbonaceous molecules, produces methane gas. We could even make engines that could take that can put canola oil in it if we wanted to. Okay, we could use the canola oil. That's a source of energy. You're being short-sighted. All these carbon chains. When we talk about energy in a material, we're talking about the energy that's. Hang on, we're talking about the energy that's hidden. That's basically hidden in the carbon bonds. Okay, and when you break that, it releases a whole bunch of energy, right? Just like when you put petrol in your car. When you petrol is octane. Okay, so 8 carbons in per molecule. 8 to 12, because this petrol is not pure. All right, so 8 to 12 carbons. The amount of energy that's released just from a few molecules, breaking those bonds of a few molecules to create carbon dioxide and water, that's a tremendous amount of energy that releases. Okay, that's enough energy to make a piston go up and down, drive a car. That's a huge amount of energy that's tied up in the biomass.
But still, I'm gonna lose reception, but you're not really thinking this through. As soon as I get reception, I'm about to lose it right now.
I didn't get what you said. Yeah, so you asked me where biofuel comes from. Anything from anything that was once alive, pretty much. Okay. Unfortunately, the other stuff's cheaper. It's easy to get. Don't have to spend much money. The infrastructure's already there. Don't have to climb that hill. That's the problem. But one day, I'll mark my words, you will climb that hill. It won't be me. Probably won't be you. But people in the future, they will climb that hill by force.
I'm just kind of surprised that with the immense amount of oil and biofuel that we would be able to have access to, that there isn't some sort of standard that allows for these types of vehicles to be mass produced. Because the diesel motor is very versatile. Yeah. And it seems like they're pushing us away from diesel for the sake of going green. But in reality, all these additional checks and balances for this like gasoline option, it seems to be, I don't know. It's just like creating an industry when we already have one.
100%. It's by design. It's by design.
Let me get in real quick.
Okay.
Yeah, go ahead, Len.
All of this oil,
this guy just wants to give it up.
Has to be used up. They're not gonna be serious until there's none.
Phil, you have Lion turned down because he's been trying to get in for a while. I don't know if you can hear him.
Yeah. Okay.
I'm just trying to be respectful. Phil's pretty cool. I've talked to him before about.
Yeah, he seems pretty cool.
Fertilizer and no-till farming and algae blooms.
Yeah.
Right?
Yeah,
remember me a while back?
It's a biofuel. Yeah, I do. Yeah. Algae blooms are a source of biofuel. We could use that.
I know, but hold on. the thing is, right, when you study geology, right, how oil is actually produced, coal, lignite, peat moss, right? This comes from living matter. Oil comes from living matter. It's a natural chemical reaction that occurs in the earth.
And coal. Yeah.
And coal.
Yeah, it does.
So this is we're already using, right, something that's a natural process where the earth turns living matter, decomposed matter into fossil fuels. Now, I'm not saying they're from dinosaurs. That's not what I'm saying. Majority of fossil fuels, including methane, natural gas, oil, petroleum, comes from plant matter.
They come from plankton. Yes, and
plankton.
All right, plant matter creates carbonaceous materials like coal, peat, all that sort of stuff. That's what plant. Animals, which is mainly plankton.
We don't know that.
Is what creates the oil. Okay, we do know that
they don't know that. They don't know that for a fact.
We do know the difference. No, we know that the fat stuff, that's the oil. We know that comes from something that was once animals. Now, we're not suggesting that comes from dinosaurs. We're suggesting that comes from the plankton.
No, I know. For some of the flat earthers listening,
there's much more massive plankton than there is of any other type of animal.
But basically, when you have a global flood or some type of cataclysm where you have immense amounts of water, right, pressing down on swamplands, forests, right, all that got swamped up and it created the oils that we see today.
Not oil, gold.
All of it.
Plants create coal.
Yep, dude. All right.
Not oil.
I'm not going to get into it right now, but the point, it does, if the pressures are high enough and the temperatures are high enough, it will create oil. The difference between oil, the only difference between oil and coal is at what depth